I'm Ryan. Today I'll be discussing this crystallization problem with a solution in heat transfer. So the problem is lactose syrup is concentrated to 8 gram lactose per 10 gram of water and then run into a crystallizing bath which contains 2,500 kg of the syrup. In this bath, it will be cooled to 57 degrees Celsius from 57 degrees Celsius to 10 degrees Celsius, and the lactose syrup will crystallize. Some of the lactose will crystallizes with 1 molecule of water of crystallization. The specific heat of the lactose solution is 3,470 joule per kilogram per degree Celsius, and the heat solution for lactose monohydrate is negative 15,500 kilojoule per kilomole. The solubility of lactose at 10 degrees Celsius is 1.5 gram per 10 gram water. Assume that 1% of the water evaporates and that the heat loss through the bath walls is 4 times 10 to the power 4 kilojoule. And calculate the heat to be removed in the cooling process. And we can easily visualize this with a diagram. So here's my diagram. Now, our lactose syrup will be cooled from 57 degrees Celsius to 10 degrees Celsius. Upon cooling, some of the lactose will be crystallized into lactose monohydrate. And because at 10 degrees Celsius, the solubility of the lactose is 1.5 gram per 10 gram of water, and some water will become vapor. And it is said that 1% of the water will evaporate. We were already given the specific heat of lactose solution are already given at 3,470 joule per kilogram per degree Celsius, and the heat of solution for lactose monohydrate is negative 15,500 kilojoule per kilomole. And molar heat solution of a substance, the heat absorbed or released when 1 mole of the substance is dissolved in water. And the heat loss through the bath walls is equals to 4 times 10 to the power 4 kilojoule, is our Q bath. And what we need to find is the heat to be removed in the cooling process, or the total heat. And now the first thing I'm going to do is do an overall mass balance. Overall mass balance. So feed is equal to liquor plus vapor plus crystal, and this is our overall mass balance, or 2,500 kilogram of syrup is equal to liquor plus vapor plus crystal, or the lactose monohydrate. Now we can get the vapor since the problem said that 1% of water in the feed is water vapor. So 1% of what equals B equals 0.01 times 2,500 times 10 gram of water over 8 gram of lactose plus 10 gram of water, since this is our mass fraction of water in the feed. So vapor is equal to 0.01 times, so this will be equal to 1,388.89 kilogram, or our vapor is 13.89 kilogram. So now our overall mass balance is now equal to 2,500 is equal to liquor plus 13.89 kilogram, vapor plus crystal or of lactose monohydrate. what I'm going to do next is do a lactose balance, and I already write it here because it won't fit in here, this part here. So our lactose balance is the XF. Our variable X here is is the mass fraction of lactose in the feed, like liquor and crystal. So this is our lactose balance. And XF, we can get the mass fraction of our lactose by using the solubility at 57 degrees Celsius and 10 degrees Celsius in the feed and at liquor. So 8 gram over 10 gram plus 8 gram, it would be equal to 0.4444. That would be the mass fraction of our lactose in our feed at 57 degrees Celsius. And the mass fraction of our lactose at 10 degrees Celsius in our liquor is 0.1304. Now, next thing I'm going to do is do the mass fraction of our lactose do the mass fraction, get the mass fraction of lactose in the crystals. So XC would be equal to molar mass of lactose over molar mass of lactose monohydrate, and molar mass of lactose is 342 grams over 360 grams. 360 grams is the molar mass of lactose monohydrate, and this would be equal to 0.95. So now we get our mass fractions in every exit of our lactose. Then let's calculate our lactose balance. So 0.444 times 2,500 kilogram is equal to 0.1304 times our liquor plus 0.95 times crystal. Now 0.444 times 2,500 kilogram is equal to 1,111, equal to 0.1304 L plus 0.95 C crystal. And we can get our L and C, or the value in the liquor and the crystal, by using our calculator by two unknowns, and the value of our liquor in our liquor is 1,526.12 kilogram, and in our crystal we have 959.99 kilogram. Now we already done the mass balance. We can do next we can do a heat balance. Now let's continue to the heat balance. So heat balance is Q, total heat, is equal to the heat crystals plus the heat loss in crystallizer bath. So, and the heat in crystals is equal to feed times heat capacity times the temperature difference plus crystals times heat of solution of lactose monohydrate. This expression here is during the crystallization process, and since there are water vapor, this will be minus by the vapor, and the lambda symbol is the constant value of water. The heat of vaporization of water at 10 degrees Celsius is equal to 2,472.47 kilojoule per kilogram. Now we've already get our value of vapor and crystal, and the other constants are given. We can already get the Q crystal, the heat. So F is equal to 2,500 times the heat capacity of lactose, so 3,470. Since this is joule per kilogram per degree Celsius, we'll be converting this to kilojoule per kilogram. So divide by 1,000 times the temperature difference, equal to 57 minus 10 plus the amount of crystal. The amount of heat in crystal is 959.99 kilogram times 15,500 over, and we'll be converting this into kilojoule per kilogram, since this is kilojoule per kilomole, and per 1 kilomole there will be 360 kilogram of lactose monohydrate. So minus the heat absorbed by water becoming vapor. So the mass of water vapor is 13.89 kilogram times the heat of vaporization, so 2473.47 kilojoule per kilogram. So that this will equal to 414,719.26 kilojoule. This will be the heat crystal. Now we've already get the total heat removed during the crystallization process. But somehow this is not that, because in the problem it is said that during the crystallization process and heat loss of 4 times 10 power 4 kilojoule in crystallization bath. So the total heat removed is equal to Q crystals plus Q bath. So 414,719.56 kilojoule plus 4 times 10 to the power of 4 kilojoule. So total heat removed is equal to 454,719.56 kilojoule. Now we already get the total heat removed during the crystallization process in crystallizer bath.
So hello everyone. So we have a problem here, and which is an evaporation problem, and I am here to teach you how to solve this specific problem. So the problem states a solution with a negligible boiling point rise is being evaporated in a triple evaporators using saturated stream at 121.1 degrees Celsius or 394.3 Kelvin. The pressure in the vapor of the last effect is 25.6 kilopascals absolute. The heat transfer coefficients are 2,840, 1,988, and 1,420 watts per square meter Kelvin, and the areas are equal. Estimate the boiling point in each of the evaporators. So the first step to do in this kind of problem is to step 1, write the given of the from the problem. So it is stated in the given that the temperature of the saturated stream is 121.1 degrees Celsius. The pressure in the third evaporator is 25.6 kilopascals absolute, and the heat coefficients which are 2,840, 1,988, and 1,420. And it also states that the areas are equal in each evaporators. So step 2 is to write the required thing you have to find in the problem. So it is required for us to solve for the boiling point of each evaporators, which are the T1, T2, and T3. Step 3 is to draw a diagram of what the evaporator is. If you can see, it is the feed, which is the saturated stream, evaporator 1, evaporator 2, and evaporator 3, which the pressure in evaporator 3 was given. The next thing to do is to find the values in the table, since it is given that P3 is equals to 25.6 kilopascals. There's a table in Ginkgo Place which is found in A.2.9. It is the values of the saturated stream, and with the pressure of 25.6 kilopascals, the temperature in of the saturated stream is 25.6 degrees. Next is we use this formula. The summation of delta T is equals to Ts minus T3. Since we already have the value of Ts and T3, we just plug in the values. So summation delta T is equals to 121.1 degrees Celsius minus 65.6 degrees Celsius. We minus that, and the answer is 55.5 degrees Celsius. Next thing to find is the T1 and delta T1, and the solution and the formula to use for the delta T1 is the summation of delta T times 1 over heat coefficient 1 over 1 over heat coefficient 2, 1 plus 1 over heat coefficient 2 plus 1 over heat coefficient 3. Sorry for that. So we just plug in the values, and the summation of delta T here was 55.5. Then the heat coefficient was already given, so we just plug in and we find the answer. Same as delta T2, but the numerator is now 1 over heat coefficient number 2. Also in number 3, the numerator is also 1 over heat coefficient number 3. When we find these values, we use this formula. T1 is equals to Ts minus delta T1, and we already have the value of Ts, then the value of the delta T1, we just minus them and we find the answer. The reason why it is Ts, it is because in this diagram, Ts was our feed going to evaporator 1, and we are finding the boiling point in evaporator 1 first. So Ts minus delta T, 121.1 degrees Celsius minus 12.53 degrees Celsius, we find the answer. Same goes with T2 and T3. It is used T1 is used here because T1 is the feed in evaporator 2, and T2 was used in evaporator 3 because T2 was the feed in for evaporator 3. When we got the values, these are the answers.
Our third problem is evaporation. So the problem goes like this. A single effect evaporator is concentrating a feed solution of organic colloids from 5 to 58%. The solution has a negligible boiling point elevation. The heat capacity of the feed is Cp equals 4.06 kilojoules per kilogram per Kelvin, and the feed enters at 15.6 degrees Celsius. Saturated steam at 101.32 kilopascal is available for heating, and the pressure in the vapor space of the evaporator is 15.3 kilopascal. A total of 4,536 kilogram per hour of water is to be evaporated. The overall heat transfer coefficient is 1,988 watts per meter squared per Kelvin. What is the required surface area in meters squared? And the steam consumption. In our problem, the givens are we have the overall heat transfer coefficient denoted as U is equals to 1988 watts per meter square per Kelvin. And the other givens are illustrated in our FBD. So in our feed at 15.6 degrees Celsius, we have an organic colloid of 5%, water is equals to 95%, and a Cp of 4.06 kilojoules per kilogram per Kelvin. And we also have a saturated steam that is entering our evaporator with a pressure of 101.32 kilopascal and a pressure of 15.3 kilopascal in the vapor space of the evaporator. Leaving our system, we have 4,536 kilogram per hour of evaporated water and organic colloid 50% and a water of 50%. This problem required to solve for first is steam consumption, then second is the surface area. So in our solution, the first process is finding the overall material balance. It is an application of conservation of mass to the analysis of physical systems by accounting for material entering and leaving a system. So in our equation, we have F, which is the feed. It is the one who's entering to our system, as we can see in our free body diagram, is equals to 4,536 plus L. 4,536 is the water vapor that is leaving our system, and L is consists of the solute and the water. So since we have two unknowns, we have the feed and the L, we're going to proceed to solute balance, enable for us to find the unknowns in our first equation. So we're going to multiply the feed to 0.05 since there is a 5% of solute present in the feed, and 4,536 times 0 because there is no solute together with the evaporated water, as we can see in the FBD. Then after that, we're going to add L times 0.5 since there is 50% organic colloid present that is leaving the system. So to find the value of F, we have to combine 0.5 L over 0.05, so we can get F is equals to 10L. So enable for us to find the unknown, we're going to substitute those equation in our first equation. As we can see, as we solve in our first, we have F is equals to 10L. So we're going to write 10L is equals to 4,536 plus L. As you can see, we only have one unknown, so we can solve for the value of L, which is 504 kilogram per hour. Next, we already solved for the value of L, and we're going to solve for the value of F. As we all know that F is equals to 10 times L, so we can get 540 kilogram per hour. The third step is solving for heat balance. In the appendix 2 to 9 of Jen Copla's book, at 15.3 kilopascal, temperature 54.33 degrees Celsius, we have an enthalpy of the vapor of 2,599.72 kilojoules per kilogram. And we have an enthalpy of the saturated vapor of 2,227.43 kilojoules per kilogram. Since in the rule, we all know that total heat enter is equals to total heat leaving the system. So we're going to use the equation heat in the feed plus heat in the steam is equals to heat in the concentrated liquid plus heat in the vapor plus heat in the condensed steam. That is with that equation. Since boiling point elevation is negligible with 0 degrees as the basis, then we should use latent heat of evaporation. So in our first equation, we're going to cancel the SHS. We have our new equation, which is the enthalpy of the feed plus the latent heat of the steam is equals to the enthalpy of the liquid plus the latent heat of the vapor. So we're going to find the value of the vapor, the latent heat of the vapor, and the equation would be HV, or enthalpy of the vapor, subtracted by small letter H, with a V, which is the latent heat of evaporated steam vapor, which is equals to 227.43 kilojoules per kilogram. So we're going to subtract the values, and we're gonna have the answer, which is 2,372.3 kilojoules per kilogram. So next, at 100 degrees, the latent heat for steam is 2,257.1 kilojoules per kilogram. Enable for us to find the value of S, we're going to use the first equation, or the overall material balance, in solving. So we're going to use 5,040 kilogram per hour, which is our feed. The value of our feed, of our F, is multiplied by 4.06 kilojoules per kilogram per Kelvin, which is the value of our Cp, and multiplied by our change in temperature. We have 15.6 minus 54.33, and we should add it to our S, which is an unknown, multiplied by its latent heat, 2,257.1 kilojoules per kilogram, is equals to 0, plus the vapor, 4,536 kilogram per hour, multiplied to its latent heat, 2,372.3 kilojoules per kilogram, and we can solve the answer, which is S equals 5,118.63 kilogram of steam per hour. So to solve for our second required in the problem, we're going to use the equation Q is equals to S times latent heat. Since we already obtained the value of our steam consumption, which is S, we're going to multiply that value to the latent heat, which is 2,257.1 kilojoules per kilogram, and converted it to joules per second. So the answer of our Q would be 3,209,239.32 joules per second. And after that, after obtaining the value of Q, we're going to use this value in the equation Q is equals to overall heat transfer coefficient multiplied to the area times the change in temperature. So after that, we're going to substitute the values. So we have 3,209,239.32 joules per second, which is our Q rather, is equals to 1,988 watts per meter squared per Kelvin, which is our W. A multiplied to change in T, and we can have our surface area is equals to 35.35 meter square.